Thanks for being here. Thanks, of course, to MindsDB for hosting and organizing, Jorge. So nice to see you. And we are Nixtla. We are a time series research and deployment company. We have been creating this open source time series ecosystem that has different tooling, models, and solutions for you practitioners to solve time series tasks like forecasting, anomaly detection, and everything related to applying statistical machine learning and deep learning methods to time series. We're very happy and also very proud that we recently joined forces with MindsDB. We're both proudly open source companies, and now everyone can start leveraging the power of state-of-the-art time series algorithms inside their own database. So thanks to the in machine learning database capabilities of time series of MindsDB and the engines of Nixtla, now everyone, and not only experienced data scientists, can start doing time series tasks. So we are very happy about that alliance, and we believe it's gonna keep growing, and we're gonna be pushing new models and new solutions so you can keep building whatever you want to build around time series. We're also very proud that that Nixtla empowers other important open source projects inside the time series field, but also other machine learning solutions like H2.ai, Databricks, and even AWS Gluon TS. If you don't know what to do with time series, some of the use cases that we have seen in production recently are around retail. So for example, Trasio, which is a third-party reseller in Amazon, one of the biggest, they use Nixtla to forecast thousands of different items or SKUs so they can optimize their inventory. But we have also seen people in the music industry use Nixtla to forecast the performance of different albums, songs, or artists so they can plan when to release those albums or how to manage the marketing around a certain artist. We have also recently seen use cases in production for MLOps. So imagine you have different models like Lyft that has thousands of machine learning models for pricing, driver allocation, and they need to be sure that those models are working. So what they do is they model the output of those models as a time series, and if something is above or below a certain threshold, they deem that as an anomaly, and they either fix the model or go look in the world what's happening. Those are some of the examples of the things that you can build around Nixtla. Before we deep dive into the rest of the conference, we would like to take a moment to acknowledge the diversity of the company and also to take a stand for inclusion and diversity in the field. We do believe that the field would benefit from a more diverse community. Nixtla is proudly founded by members of the Latinx community, and also Fede, my co-founder, is a trans woman, so we're also happily founded by a trans person. So maybe you're asking yourself, I came here to listen about Gen AI stuff, where is that? And we're going right there. So as you better than anyone knows, OpenAI recently released a new the GPT API. There's also a wonderful API via Discord for video and image. However, there are three important elements to understand anything that has to do with intelligence or experience. What makes us human, what makes us sentient beings and intelligent beings, it's a fortunate combination of our capabilities to understand language, of course, text, speech, and those are the things that are being done by companies like Anthropic, OpenAI, obviously Hugging Face. Then perception is another important element to see, hear what's around us, and that's what companies are doing like Stability and Midjourney. But a third fundamental element that is a necessary condition to experience and a necessary condition for intelligence in general, it's time. Because the temporal dimension is absolutely necessary to understand anything that has to do with change, growth, and even decay. And furthermore, businesses, institutions, systems, they don't really speak in images or language, they speak in data. More precisely, they speak in time series. We at Nixtla are trying to build that intelligence, the technology to classify, predict, and understand time series. So the standard way of doing a time series pipeline is complex with many different roles. You have to build autoregressive features. You have to train local and global models. You have to do feature engineering, cross-validation, tiresome hyperparameter search. But what if we could have generative AI about the future? What if we could just upload our data sets like we do in other machine learning fields and predict? But what do we need to make that work? What is necessary to make that a reality? And the first thing that we would need in the time series field to make that happen, is to have deep learning models that are able to extrapolate, deep learning models that are actually able to generate on new on-scene data accurate results. But is that even possible? How's the deep learning field looking in time series? And the bad news is that academic research is not very optimistic. You can see this, it is very serious tweet from Bojan, who claims that deep learning research for NLP and computer science is amazing. It's almost indistinguishable from conscious beings, and it's using a massive amount of computation, while deep learning for tabular data and in time series too, you can beat SOTA with very basic methods. To be a little bit more serious, there has also been some important research conducted at MIT, for example, who, the short story is, claimed that transformer-based architectures loses grotesquely against very basic mechanistic models. We at Nixtla have also conducted some benchmarks. We did some benchmarking of statistical methods, the basic stuff that you learned at school, like ARIMA, CTS, autoregressive models, and very sophisticated state-of-the-art deep learning models. And we showed that a simple statistical ensemble in certain data sets, it's 25,000 faster to train and only slightly less accurate. To put it in other words, we showed that you can outperform deep learning, that deep learning ensembles outperform statistical ensembles just by less than 1% in SMAPE, in accuracy measured in SMAPE. However, it would take you 14 days to run, and it would cost you around 11,000 to run instead of 6 minutes and maybe 5 cents of computing infrastructure. So there's more research to support these claims. And there is generally an observation that is quite interesting, namely that according to some researchers, one of the basic laws for deep learning, namely the laws of scales, the intuition that the bigger the data set, the bigger the model becomes, that it doesn't hold for time series. However, on the other side, the good news is that the industry leaders have been quite successful at deploying very sophisticated transformer-based architectures and in general deep learning models. This is the case for Amazon, for example, that has 200 million SKUs across thousands of different zip codes, and they use on a daily basis deep learning-based architectures to forecast and plan their inventory. This is also the case for Google and another big retailer in Europe called Zalando. So if you see the history of Amazon, for example, they started in 2007 building very basic time series models like the ones that we showed in the benchmark, and then they started an interesting road to more sophisticated architectures, and ended up deploying in production what they call the multi-quantile transformer, which is a transformer-based model for time series. So what's happening? Why is it so that academics are so frustrated with the results and performance of deep learning models, and the industry is so optimistic about the potential to use those in production? And the answer is this cliche, namely that size does matter, at least for transfer learning, and that scale laws really need scale to actually work. And the problem in the field is that the biggest data set in academic research is still incredibly small compared to the actual data sets of the industry. So recently, one of the best teams in the field, the team in Zalando, published this article. I think this was published like 2 or 3 days ago, that actually shows that demand error does decrease if your training set size becomes larger. And this is important because the graph that I showed you before was only accounting for number of observations and not necessarily for diversity and number of unique time series. So what we're starting to see is that we actually need big data sets that are also diverse and include a wide variety of time series. So in honor of the famous mathematician David Hilbert, which we prompted here in Midjourney to wear classical pre-Hispanic attires, we created what's called the Nixtla program. And the Nixtla program is our answer to this crisis in the field, and it consists of three elements. First, we do think that we need in the field a big public data set for this sophisticated models to work. So we are creating and publishing TimeNet, which is gonna be the largest public data set for time series. We're gonna create a time series that is composed of 100 million of diverse web traffic data sources. So here the intuition is very similar to other fields in NLP and computer vision, namely scrap the internet, take public knowledge, train sophisticated models, and see how well they perform in new tasks. The second aspect of our research agenda in the Nixtla program is what we call the exploration of transferability conditions and generative capabilities of neural network methods in the field. So basically, this mathematical notation is only showing that we are trying to generate something similar in terms of foundational models that are able to be trained in one source domain on your left, and those this could be like TimeNet, and then that model or that pair of variables and probabilities is able to extrapolate to other domains like finance, IoT, or in general data that was not seen before. We are here exploring the empirical and theoretical implications of those conditions, and particularly we're interested in finding the best architectures to ensure transferability across deep learning models in the time series field. If this is successful, then the third part of the program is going to be applications. And the applications are really exciting because now everyone could include forecasting and anomaly detection in their applications without any need of Python code or even a machine learning code. They could simply call an API of a pre-trained model and do forecasting, anomaly detection, planning, and so on. The only thing that you would need is to upload your data and predict. That would be extremely fast, it would be easy, and it would be very cheap. It would also help in what's called the cold start problem. So imagine you open a new startup or a new shop and you have not history, or you don't have any history of your items. So in order for you to use classical time series methods, you would need history for the autoregressive features. Now with these pre-trained models, you could feed the model one single week or one single day of sales and start predicting. It could also help you build synthetic data generation, which would be very important for privacy sensitive applications, but also to interpolate between missing data of your own sources. So that's also very exciting. So is this feasible, or are we maybe putting too much of the wrong stuff in our pipes? And as my grandpa used to tell me, we rather show than tell. So we're gonna be very brave here and do a live demo. So we recently uploaded a demo to Hugging Face, so you can play around with it. It's now completely public. And basically what we did here is we trained an NHITS model. This is a neural network model that we created. And we trained that on a public data set called the M4 dataset. And now you are able to use other data sets that were never seen before, like for example here, electricity. And as you can see, the model is able to predict the future of a data set that has never been seen before by the model. And this is amazing because this is done in less than 1 second of computation, given that we are not training anything, we are just doing inference. And maybe you're not interested in the next 18 observation, but maybe you want to see further along in the future. Simply by extrapolating or making bigger the forecast horizon, you can start predicting the future in a generative way. You could also feed it other data, like for example, the visits of Python Manning, because maybe you like American football. And again, you see that the model is quite accurate at predicting the future in a truly generative way. So these models are outperforming classical benchmarks like ARIMAs. We're working and making them bigger and more sophisticated, but we wanted to give you a glimpse of the capabilities that you would have with transfer learning for and generative AI for temporal tabular data. And I want to finish by highlighting how excited we are to partner with MindsDB and to keep building amazing stuff together for the open source community. Thank you very much. This was our presentation.
Thank you so much, Max. Opening the floor to questions. I have a bunch if nobody else has them.
Do you have any specific use cases around weather? I saw you had energy usage prediction. Usually weather is a big factor in that, and that always has a massive data set attached to it.
Yes, we have seen weather mainly come up as what we call an external covariate, an exogenous variable, to help the accuracy of the prediction. So as you point out, one of the main factors influencing electricity consumption is weather. Given that if it's hotter, then you tend to turn on your AC, and this consumes electricity, and vice versa. Now, if it's also very cold, you turn on your heat, and that normally also consumes electricity. So we have seen weather come up as that, as like an extra element to improve accuracy. But weather forecasting is actually done with, yes, time series, but also some structural models that take into account like environment variables.
And does this work with a multivariate time series?
Yep. So if under multivariate, the short answer is yes. However, it's important to clarify that in the time series field, multivariate can mean two things. One is to forecast one time series, including a lot of different variables like weather, prices, or other time series. And yes, it works for that, but also the more sophisticated multivariate programs in time series try to model the interaction between all the different series. And that's really exciting, but it's also computational, very expensive, because you can imagine how that scales. But yeah, we have some models, some graph-based models that allow for multivariate analysis and prediction. More questions? We are more than happy.
Yes. Yeah, I've got a quick one. So can you maybe summarize like principles and techniques for pre-training, like an NHITS model, for instance? Like how would that work?
Yep. So what we did, and I mean maybe that my co-founders are here. Fede was the one that trained it. So if you mind giving her the microphone, I think she would be more than happy to explain what she did.
Yes, absolutely. So basically, the main idea behind transfer learning is that you can train a model to learn the patterns of the time series, in particular, for example, trend and seasonality, and then you can use that pre-trained model to extrapolate with a new data set. So in reality, the model is learning the patterns, the underlying patterns in the time series, and when you feed the model with a lot of time series, you can get different information, and then you can extrapolate that information for other time series.
And maybe just to complement on that, which is interesting, the demo that we showed you with the M4 competition, the M4 has around 30,000 series, so it's not very big. And we used, I think, a very large machine in AWS. We didn't even use GPUs for training because of the costs. It took, I don't know, 1-2 hours maybe, and the model can be hosted inside a Hugging Face space. So it's not really that expensive, which is it's interesting because obviously we wouldn't use these models in production. It's more for a demo purpose, but it shows that it can be done, that you can have very sophisticated, powerful models that are still not like immensely big. So as we like to see this is that it proves empirically that there's a way for us and other researchers to bring a new disruption in the field. ¿Alguien atrás tuyo?
Tom.
Great presentation, great work. Thanks to the team. Why did you use the M4 data set? Were there any advantages of using that as opposed to another one? I assume it's something to do with the variability of the series.
It's one of the standard data sets in the field, so it's very famous. It's also one of the data sets that we work a lot with. So it was, in terms of plausibility and ease, for us, it was the best choice. But the real exciting task is going to be, once we have TimeNet, this big data set, to train on that and then extrapolate. But it was out of convenience and standardization.
There are a lot of data sets available in the geophysical community, like global climate models. You can use synthetic data from GCMs to train your machine learning models on time series data. Have you tried that? And then you were also showing error bounds on the predicted time series. And depending on the model, they'll either increase at square root or n square, depending on the models that you're using. But they were pretty constant on what you showed, the error bounds. So how are you computing that?
Yeah, that's a very. The first question is, no, we haven't done used those data sets, but we're very interested in exploring them. The second question regarding, if I understood correctly, the calibration of the confidence intervals of the future prediction, it's a very interesting question. And maybe, Christian, you want to talk a little bit about how we are training for specific distributions inside the models?
Yeah, this is a really good question. In that example, the horizon was still shorter. What we observe in practice is that the longer that we're trying to predict, the larger the intervals would happen, and we observe that with our models. And in practice, what we do is our quantiles are calibrated, so we make sure that they actually represent the distribution on the time series.
And I mean, philosophically, it's very interesting. At the end of the day, what we are trying to do is, some might say predict the future, but that in itself is sort of weird. It sounds like magic. So we are rather trying to think about it in terms of quantifying possible uncertainties, possible distributions about a possible future. And there are other things that we're also exploring that are being done in other fields of the ML community, like conformal prediction for quantifying uncertainty. So that's interesting. I think there is someone there.
Yeah. Oh, Sam.
Awesome talk.
Thank you.
Very mind expanding. How many spatial dimensions are you looking at exploring in your data sets? And just to contextualize, my son is doing his PhD in nanoengineering. So it's a combination of quantum chemistry and large scale supercomputer simulation. It's obviously extremely expensive. And so they're trying to figure out how can they use models to simulate quantum chemical environments like a million atoms to figure out the electrical capabilities of novel materials. So I'm curious to get a sense of how many dimensions of spatial temporal information you want.
Absolutely, that's a very interesting question. So we right now are simplifying the problem in terms that we are only directly considering temporal dimensions, and all of the external dimensions like temporal or related series are encoded as covariates of the series. So we are handling it as a univariate or a univariate time series problem with external covariates. But we don't include dimension as a whole, it's space as a whole new dimension, which makes it a lot less expensive. And that's what's also what Jorge was asking. To be able to include space as a whole dimension, we would need to take it as a really multivariate, truly multivariate problem, and that tends to explode computationally. So that's something that we are still not fully exploring. One more, maybe?
Any other questions? Yeah, I think one more, and then we have a break and prize draw.
We're also going to be here at beer time, so happy to take a beer and speak with you more.
Oh, Patricio.
No, Patricio, your question is gonna be too hard for me.
All right, get ready.
No, amazing presentation. I just wondered, like, in terms of, you mentioned conformal prediction for uncertainty. Have you guys run any large-scale experiments? If so, have you gotten any findings in terms of like how this stacks against other, let's say, I don't know, quantile laws or something that's more baked into the model?
Yeah, we don't have a conclusive answer. Just yesterday, we were sort of fighting inside of the team if we should rather quantify uncertainty with conformal predictions or by targeting directly the different quantiles. Christian was defending the quantile approach and Fede was defending the conformal prediction approach. So we don't have a definite answer there.
Thank
And
you.
if I say something, I might like cause a problem. So I'm gonna be political here.
Okay.
Thank you.